Hello, everyone, and welcome to Ketiv Virtual Academy. My name is Tyler Hart. I'm with the marketing team involved with running these weekly training and thought leadership sessions. And today's topic is RF and dielectric heating simulations using Ansys, HFSS, and Icepak. Your expert today is Graham Stevens, application engineer here at Ketiv, and he'll be here to talk through everything and answer any questions you have. If you have any questions during the session, please submit them through the Q&A button at the bottom of the screen. We'll either address them during the session or at the end. And also, all of these sessions are recorded and available on ketiv.com or our YouTube channel. You will also see at the end of the session, we have some upcoming events. We have obviously a KVA next week. And we also have a series of in-person events coming to a city near you. Our traveling manufacturing innovation workshop will bring together leaders like you to connect with each other in person on recent developments in workforce management, customer experience, manufacturing technology, you name it. So stick around, scan the QR code, and get signed up for one of those. But without further ado, I'll pass things over to Graham to kick us off today. Thanks for being here, Graham.
No problem. Thank you, Tyler. So good morning. This is Graham Stevens from Ketiv, here to talk about RF and dielectric heating simulations using Ansys. And when we think about dielectric heating, Ansys has a number of different modules, HFSS, Maxwell, Icepak, etc. And to do RF heating, typically we would combine two different modules, HFSS to give us the RF heating and joule heating losses associated with the high frequency analysis. And then we pass those losses to a thermal package, which could be AEDT mechanical, steady state thermal, or it could be Icepak, or it could be Fluent for that matter. But for today's presentation, I'm going to focus on AEDT mechanical and the whys and wherefores you would use one versus the other, and then especially on Icepak. Relative to thermal, which thermal package to use for electronic packages, for electronics when you're marrying it with HFSS. There are, this slide sort of shows sort of which one might be applicable, which one might not. So typically AEDT Icepak is capable, has higher amount of capability, but in some cases AEDT mechanical can be useful. So if you're at a steady state where the boundary conditions and heat flow is in a steady state, then you could consider using AEDT mechanical. But Icepak can also handle changing boundary conditions and heat flows. And then it really depends on the type of heat transfer mechanism that you are wanting to model. So if you're just doing a conduction analysis, AEDT mechanical may be more suitable because it's slightly faster than Icepak. But if you're doing a convection analysis where you know the heat transfer coefficient on a particular surface, then you can use AEDT mechanical. But if you're doing a full CFD convection analysis, whether that's air, natural convection, or whether that's water cooling, then you would want to use Icepak. And similarly, if there's radiation involved, you would want to use Icepak, at least at the moment. And so when we think about coupling the RF heating and Icepak, we need to think about whether it's a one-way coupling or a two-way coupling. And for dielectric heating, this you can sort of see to the right some material properties relative to dielectric constant as it changes versus temperature. So for liquids, water, of course, changes a fair bit with temperature. But this sort of shows some other liquids here and the changes. And this bottom four graphs show for four different frequencies, 1 kilohertz, 1 megahertz, the relative permeativity change and the change in dielectric tangent, and for a particular plastic, in this case, a PPS. And you can see that, to some extent, the relative permittivity doesn't change very much versus temperature. And so if you have a really high temperature change where these sorts of the relative permeability is changing enough to matter, then you would want to consider two-way coupling. But for the most part, for RF heating, one-way coupling will be sufficient. But for today, we'll be doing both, just to sort of show you how to go about doing both. And along those lines, when you're doing two-way coupling, you have to have a really good sense, or not sense, but good material data associated with how does the electrical conductivity change with temperature relative to Joule heating, and how does the dielectric loss tangent and dielectric constant change versus temperature. And you can see for FR4 here, and this reference, which is just one of many, you have to find your own material data here. The change in temperature is not great, and so if you're in a relatively small temperature range, again, you may want to just consider one-way coupling as opposed to two-way. All right, and with that, I'm going to shift now to HFSS. So this is a model here where I just have a standard twisted waveguide, and I've created an aluminum wall which has a certain thickness, and then inside that wall just a cavity of just RF4, just as a typical dielectric. And for this analysis, we've got a port on one end here. Sorry, let's see if we can get that a little better represented. So we have an input port there and an output port on the other end of the waveguide. And we're just transmitting, in this particular case, I'm putting in 5 watts of energy into the input to see how much is that going to heat up the RF4 relative to dielectric heating, as well as the aluminum Joule heating will also be taken into account here. Let's see, what else can I? So relative to the HFSS setup, we're running this at 30 gigahertz, relatively high frequency, which is appropriate. If you're doing more of an induction heating problem, you're probably at lower frequencies than that, in the megahertz range or lower. And Maxwell might be a better package rather than HFSS in terms of conducting that sort of analysis. But we're doing sort of the standard solve for these type of HFSS problems, direct solving here, and definitely saving fields, which I'll get into in a minute. So in terms of setup, the geometry construction, I did sort of the standard subtract and Boolean operations relative to model construction, where we're uniting and subtracting, intersecting, and so forth. The only sort of funky thing here is doing, let me see here. Sorry, let me just show you here. And this one is not showing up. Why not? Okay, there we go. So this is just to create this particular object. I'll change this to a model object so we can see it and model it. And now I've selected my rectangle here and my polyline. And this is just for the twisted section. We're going to use this sweep along path here and do an angle of twist of 90 degrees. And this is going to take this rectangle and sweep it along this path so that we get the twist. And so this is how this twist object is created. in case that's useful relative to your modeling. But otherwise, we're just creating simple objects, boxes, and subtracting and so forth to get our both wall of the aluminum and the cavity inside for the FR4. You can also, relative to geometry creation, of course, import parts here or use space claim to import geometry as well. And let's see, so we covered the material geometry port setup. I think we're good to go. At this point, we simply analyze the model and ensure that it's validated. And then there's a couple of other quirks that are useful relative to this kind of two-way coupling. One is we want to calculate the actual losses, the surface losses and the volume losses directly in HFSS and have that as an output, which we can then check against what losses are getting put into the Icepak analysis that we're going to couple this to as just a double check. And so to do that is a couple of operations. So one, we're going to go into the fields calculator where we go to field overlay, right click and calculator here. And this brings up the fields calculator. And for our surface losses, let's see here, we're going to look at do quantity, surface loss density, and the geometry has to be a surface geometry. So I'm going to pick on the surface. And in this case, we're doing the surface loss density of the wall, the aluminum wall, and press OK. And now we press an integral button here to take the integral. And then we add this as into the calculator. So this might be surface losses 2. And you'll notice that got added to the list here. And now this is a field calculator variable that we can use use to create an output variable to then get some results in a table. And I did the exact same thing for volume losses. We used to use the volume loss density, and in this case, the geometry, the volume geometry of the cavity, and press OK here and integrate. And we save that as a variable here. And that enables us to calculate those two quantities. And then we go into results and output variables and change this to fields because we're calculating in the fields calculator. So now the calculator expression, the surface losses and the volume losses that we just were calculating pop up. We can now insert the surface losses into an expression. We're going to call this surface loss 2 and then add it. And so you notice I have surface loss 2 here, which I'm just going to delete, but you can get the idea in terms of where this came from. Do the exact same thing for the volume losses, and then we'll create a total loss of the surface loss plus the volume loss here, where I just add another variable in that's summing the two up as well. So this creates our output variables for the analysis. And then we can insert, we create a fields report and a data table. And now we go to output. So you can output the surface loss, the volume loss separately if you want, but I created these output variables so that we can get the total as well. So I simply select all of these and do a new report. And now the program will calculate these losses when it does the analysis. Okay, so once those have all been set up, that's your setup for in the HFSS realm. We can also plot the surface loss density or the volume loss density, or of course electric fields if we're interested in the electric field, as well as your standard S parameter plot output for a waveguide. With that, we would generally just analyze the model. I'm not going to run that now. It's been run here in this one. And then we'll get at your standard S parameter plots. We'll also get an output of what our losses are. So in this particular case, the surface losses, which is the joule heating on the aluminum, is 0.09, and we can see the dielectric loss here is much higher with a total loss of 4.17. And we can look at those, if we're interested in the field here, we can look at the surface loss density in terms of, where those losses are occurring in terms of resistance, and then similarly for volume loss density here in terms of the dielectric heating. So this allows us to get a better sense of what's going on physically in terms of the heating. So then we want to now take this entire analysis and bring it into Icepak. And so to do that, I'm going to select all of my bodies. So I select, we're going to start by inserting a new Icepak analysis design here. And then from the one-way, I'm going to select all of my bodies. So select all on model. And now I copy these. Select all, just copy with a Control-C. And then I go to the Icepak design and I do Control-V to paste them all. And so now we have the exact same geometry in both analyses. I'll change this to isometric and fit all so we can sort of see things a little better. You can see I have this dummy geometry. Obviously, I'm going to get rid of that. Here, let's just do that now. Okay. And then for the Icepak analysis, we need to now describe in the Icepak design the thermal conditions under which this object is going to be subject to. So in other words, is this in open air? Does it have a cooling plate that is that it's being cooled by? What are the boundary conditions? And so I'm going to just switch to the pre-done analysis here. And so for this particular model, and let's do the orientation so we can see this a little better again. I basically created a larger box, an air box around it here for the region. And then I created an inlet here and an outlet there. And I'm just going to blow 1 meter per second squared air from one end to the other as I'm basically to cool this, as just an example flow. And of course, if you're familiar with Icepak, there are many different types of thermal boundary conditions. We can, this is where we're putting in our thermal boundaries of openings, which are the input and output I just talked about. But you can add sources, you can add walls, etc. And then the key to the coupling, and right now we're just showing how you would couple this manually, is we select the bodies that we want to couple, in this case, the wall and the cavity, and then we assign thermal, and we do EM loss here. And this EM loss, and I'm going to just go to the properties here, or something that's been pre-assigned, has a link associated with it. So there's a setup link that says, okay, I'm getting these EM losses. Now, where is that coming from? And so we go to this setup link and make sure you've picked the right analysis, the right HFSS analysis to say, this is my one-way Icepak analysis. I'm going to grab the losses from the HFSS one-way analysis. Have these checkboxes here in terms of simulate source design as needed and preserve source design solution. Make sure your variables that you might have are mapped, and double check on your frequency of operation here. And of course, press OK for all of that. And then press OK here relative to your EM losses. So that sets up the link between Icepak and HFSS. And you are then, we then need to set up the meshing for Icepak. So this is a standard setting up of a mesh region here, where I'm just doing multi-level meshing to 3 levels and getting our size correct. I'm not going to go into more meshing relative to Icepak, but you can go right-click here, generate mesh to view it, and then, sorry, generate mesh to generate the mesh, and then view it here to double check on your mesh. And then under setup, we need to, again, tell Icepak, what are my thermal conditions? And so typically I will start with these defaults at the bottom. So we have forced convection or natural convection, mixed convection or conduction only, standard defaults. In this particular case, I'm just doing forced convection. And then I am having my input here, 1 meter per second of velocity in the x direction. That's sort of my input condition. And typically leave all the defaults as they are. And then we are ready to run. With this EM loss coupling, one-way coupling is sort of sets up the link between the new 2 analyses. I would then right-click here and analyze. And then you would also do some field overlays where we want to see what the temperature field is and the velocity field of the analysis, and also do some double checking of, did this thing come through properly or not? So when we start looking at the results now, we get temperatures that look like this. So we have higher temperatures right where my 5 watts is getting applied. And then we also, here, let me turn these plots off. Let me turn the velocity on. You also want to sort of check your velocity. So we can see how we get a higher velocity around the edges, and it's relatively low velocity, or sorry, relatively high velocity here, and then it slows down a bit as it goes around, etc. So we can sort of see how the velocity is changing and make sure our air box is large enough as well, especially for in natural convection. So then another double check that's very useful to run, in addition, when we're looking at solution data for Icepak, of course, we want to look at our residuals and make sure those are correct. But also in the profile associated with two-way analyses, if we scroll up in the profile, we can, when it does the link, it will take a look at, it will output the surface loss and say, what loss am I using for, what loss is the input for Icepak? So in this case, we have a total loss of 4.1747 watts here showing in the profile. And this is where we would go back to the output table for the one-way HFSS and make sure that 4.17 is accurate here. And if not, something's off and we need to, take another look in terms of setup or something, or call us here at Ketiv to help figure out what's going on. And that would be at support@ketiv.com. So that is how you then get temperature for our waveguide, depending on what environment it's in. And then if you're thinking that two-way analysis is required, the process is exactly the same with a couple of differences. So for a two-way analysis, I basically just copied this one-way analysis here and pasted another copy into the design here. It's grayed out because I didn't copy, but and grab basically a second copy of the one-way analysis. And now I'm just going to go over a number of the changes we need to make to do a two-way analysis. So the first change we need to make is in the materials. So for a two-way analysis, we have to have in the material properties a variation with temperature. And our typical material properties, if we look at the material here, and I look at all properties so I can see them all. Your typical database will have a thermal modifier, and you can see here the thermal modifier has been defined for this two-way aluminum T4 on material. But typically it's not. It's called none. You can sort of see how most of these are none. And for a two-way analysis, we have to have that thermal modifier defined so that you have variations in material properties with temperatures. Otherwise, there'd be no point in running a coupled analysis. And so we would simply clone the material property, the material without a thermal modifier, clone it, save it, and then come into it here to edit and add in material properties relative to things that vary with temperature. So in this particular case, I have all properties here, and I have a couple of PML curves, and these were taken from Ansys's Granta materials. So another possibility, especially for some of these thermal properties that vary with materials, is to use Granta materials. To access that here within AEDT, we click on the triple dot in the upper right. And then we have this Granta materials data for simulation. If we select on that, the Granta materials will show up and we can use those. Or you can just define, through formulas what you were, how things vary. So especially here, where I'm looking at my FR4 epoxy, for instance. So I defined an FR4 on, and then based on the formulas I was showing earlier in the slides, I added these two formulas in for the relative permittivity changes with temperature and the dielectric loss tangent change with temperature, so that those are in the analysis. So that somewhat takes a little bit of time. Hopefully Granta will help. Sometimes, especially in the RF side, it's difficult to find data associated with dielectric properties changing with temperature, or loss tangent properties changing with temperature, but that's required for this type of two-way coupling. And then the other thing that we will need to do is to tell both HFSS and Icepak about these new material properties that are changing. So for that, we go to our solution for the two-way coupling now, HFSS, and right-click on that and set object temperature. And when we set object temperature, we're going to click on a couple of check boxes: include temperature dependence and enable feedback, to allow us to make sure that we're coupling appropriately relative to material properties and temperature. And then the other change, so then we do the exact same Icepak coupling where we copy this one-way analysis and paste it down here. And the only other changes on the Icepak side is on the setup. We need to right-click on our setup here and add two-way coupling. It's grayed out right here because I've already done it. But this two-way coupling, you then set some properties relative to the number of coupling out iterations and continue these settings for coupling. So this needs to be set within Icepak. And that's it. You've now, the only other thing is once we copied and pasted this Icepak two-way analysis here, we need to go back to our EM loss here and properties and edit the setup link, where we edit the link. And now we need to change the source design. When we just copy it, it's going to be showing it's going to be pointed at the one-way HFSS analysis, and we need to point it at the new two-way HFSS analysis to make sure those two are linked up properly. So once all of that is set up, we can then analyze and run. And when we do that, we can see, whoops, sorry, got too much stuff open here. Go back to can look at the temperature for the two-way analysis now. And let's go ahead and close all of these and just look at two plots together. Oops, let's title it vertically and change our orientations a bit so we can see it better. So we can now see that with the one-way analysis, the maximum temperature was kind of 200, here at the entrance. With the two-way analysis, we had a change in condition here, which the max temperature goes up slightly. And so obviously that made a difference in the answer, and then two-way coupling was worth doing in this particular case. And obviously the two-way coupling method does require a little bit more time relative to analyzing, because it does two-way. So basically it'll run HFSS once, and then it'll do it twice, or the iterations, it'll basically run it 2 or 3 times. And so you have a slightly longer calculation time relative to having to run these analyses multiple times to have appropriate coupling. And with that, I believe I've finished the demo, and I guess I want to just sort of pause here if anybody has any questions. Okay, I'm not seeing any questions. All right. So I'll now go back to my slides here. Sorry, the slideshow. All right. So if you're interested in Joule heating as opposed to dielectric or RF heating, there's a similar YouTube video that goes, or similar KVA that goes into Joule heating. It's based on Maxwell as well, but both Maxwell and HFSS act pretty much the same, so it'll apply for HFSS. We did Joule heating here. It was part of the coupling losses. It's those surface losses. So you've sort of seen it in HFSS as well. As I mentioned, if you're interested in induction heating, Maxwell is more applicable, and there is a Ansys Innovation course on coupling Maxwell and Icepak that is useful. I just wanted to also make you aware that there's an electrothermal ACT automation that helps. Right now, this particular video, we did a setup, a manual setup, where we're manually setting up those the coupling for the EM losses. There is an ACT that will set that up more automatically for you. And so that may be of interest if you're doing a lot of these sorts of analyses. And then there are, of course, other Icepak and electrothermal workflows and courses within ALH. And if you need assistance on any of that, please do not hesitate to reach out to support@ketiv.com. That's what we're here for. We're happy to help. And then in a similar vein, I wanted to alert you that Ketiv also offers simulation consulting expertise. In addition to helping you do it 100%, we also can do analyses for you. So if that's of interest, in terms of hiring external consulting, we do structural analysis, fluid dynamics analysis, and electronics analysis of all types, sizes, and shapes. And again, if that's of interest, please do email us at support@ketiv.com. I'll be happy to help there. And then the last thing I wanted to say is that we have some upcoming sessions on September 14th. There's another KVA on navigating blocks in AutoCAD's next-gen workflow. And as Tyler mentioned, in October, November, Ketiv is doing manufacturing innovation workshops in person. And if those are of interest, please do scan this QR code, and we'd love to have you participate. And any other questions, please contact me directly at grames.stevens@ketiv.com or course marketing@Ketiv. And thank you so much. Really appreciate it. Any other questions coming through, Tyler?
Looks like we're good on questions at the moment.
Okay.
Graham, thank you so much for all of your time today. Always a pleasure. This will be posted on our YouTube channel as well as in the historical KVAs on our website. So be sure to check those out, share them with peers, and we'll see you next week. Thanks so much, Graham and everybody else.
Take care. Have a good one.